How can we keep track of all the data that we collect on scientific expeditions into the Arctic? This channel is called Nansen Legacy Data Management. I use it to provide data management training and information primarily to people involved in the Nansen Legacy project. But a lot of the content that I discuss is actually relevant to a lot of people outside of a project and across the whole of academia in some cases. So perhaps you're watching this video and you've never heard of a Nansen Legacy project. I'm a data manager and I work as part of the Nansen Legacy project, named after the great Fridtjof Nansen. Fridtjof Nansen was arguably one of the greatest figures in Norwegian history. He was a scientist, a diplomat, a humanitarian, and a Nobel Peace Prize winner. But perhaps most famously, he was an Arctic explorer. Nansen began scientifically exploring the Arctic Ocean way back in 1883, leading the Fram expedition. 125 years later, 10 Norwegian research institutions came together to follow in his footsteps in the Nansen Legacy project. Today, the northern Barents Sea is one of the fastest warming places on the planet. We can see this from the increase in the heat content of the ocean since the turn of the century. The Nansen Legacy project explores what impact this climate change is having on the northern Barents Sea and the life that lives there. We do this through multiple research expeditions, many of which take place on Norway's new icebreaker, Kronprins Haakon. The project is huge and involves around 280 researchers, students and technicians. It's multidisciplinary. It includes geophysicists, biologists, chemists, engineers, meteorologists, oceanographers, geologists, probably more, and they all together collect a wide range of different data. As data managers, it's our job to develop and manage systems that can keep track of all of this data, and will also make it easier for researchers to publish their data in such a way that those data can be reused by the next generation of scientists. But this is really tricky, particularly in such a large and multidisciplinary project, because different disciplines follow different standards and conventions, and so the system we develop has to consider all of them. But this multidisciplinary nature of a project makes it all the more important that we have a single system in place to keep track of everything we've been doing in a consistent and standardised way. So we can make the biologists aware of what the geophysicists have been doing. We can make the oceanographers aware of what the meteorologists have been doing. This all promotes multidisciplinary collaboration, both within the project and also outside of it. So what do we do? Well, firstly, I can't take all of the credit. The system was actually developed by Pål Ellingsen, who was previously in my role. I've just developed it a little bit further. He now works at the Arctic University in Tromsø. So how does it work? Well, firstly, we've developed a spreadsheet template generator, which helps us log all of the samples and the sampling activities in a standardised way. The template generator looks like this. You have a long list of fields that you can select from. Some of these fields are required, so everyone has to include these, and this means that every sample or sampling activity has some common metadata that we can later search by. Many of these terms are based on the Darwin Core standard, which is used for recording biodiversity data. But there's also a lot of terms that have been taken from CF standard names, and there's a bunch of other terms that are based on whatever people in the project are working on. So this list of terms is quite extensive. Each term is accompanied by a description, and maybe some instructions on how to fill it in, and sometimes some examples. Using a system like this ensures that all the samples and all the activities have been logged in a somewhat consistent way. And this is absolutely vital if you want to later create a searchable catalogue which allows someone to come along and search for all the samples that have been collected on a certain day, or from a certain place, or all the samples of a certain type. So the researchers go ahead and select whichever terms they want to include and hit Create Template. They can then download a template that includes a separate column for each of these fields that they've selected. The descriptions are visible as notes whenever you select a cell. And we've made some efforts to standardise how certain fields are filled in. For the sample type and the gear type, you have to select from a drop-down list. Some columns have formatting restrictions, like the coordinates. They have to be numbers, for example. There's also this sampling protocols column. So, as a project, we've also published documents that describe the sampling protocols that we follow. So these are basically sort of like step-by-step instructions on how all the different types of data have been collected. So let's say that someone's interested in this sample, this fish liver that's been collected. This is logged with version 4 and section 11.4 of the sampling protocols document. So they can navigate to that document and find exactly how that sample was collected. But also, this tries to ensure that two different people on two different cruises are collecting the same sort of data in exactly the same way, which makes their data more reliably comparable. So the researchers go ahead and fill these in, one row per sample. We log all physical samples, like one row for each fish that we've caught. And then we also log one row for each activity. So for example, each net cast that different fish were collected in. Or any instrumentation that's been recorded for that matter. Or even some mission onto the ice, so we can log a single ice station as one activity. We also have label printers on board, so researchers can label each physical sample. Researchers can write whatever they want onto this label, but the key piece of information is the data matrix. If you scan this, you get this. This is a UUID, or a Universally Unique ID. So a UUID is a 32-digit hex number. That means that it's 32 digits long, and for each of those digits is one of the numbers 0 to 9, or one of the first 6 letters of the alphabet, A to F. This is a robust and reliable way to ensure that you can uniquely identify each sample. So the researchers go through and attach each of these labels to all of their samples. They then plug in a scanner into their computer. They can select a cell in the event ID column where they want the UUID to appear, and then they hit the trigger on the scanner. So now the physical sample and the electronic log are linked. So years into the future, if someone finds a sample in a freezer somewhere, they too can scan it, find this UUID, and then find all the metadata that's been recorded, which is far more than you can include on a small label. And this will help them discover what that sample is, when it was collected, and who it belongs to. But there's more. The metadata catalogue that we've developed is hierarchical. Let's take an example where we've logged a fish that we've collected. It will have an event ID for itself, but we can also record alongside it a parent event ID. So this is the event ID of the net cast that the fish was caught in. So you can see that we have this hierarchy where we have the net cast at the top, and below that we have all the fish that have been collected in that single net cast. Each of those fish will be logged with the same parent event ID, which is the event ID of the net that they were caught in. And we can have some more levels if some of the fish have been divided up into different pieces, for example. This is quite a lot of work for all the researchers. But the good news is that they don't have to record everything all by themselves. You see, the vessel, Krompen Tokon, actually has its own onboard cruise logger that keeps track of all the activities that have taken place. These are the things at the top of the hierarchy, so things like the cast of a net, or deploying a CTD, or a drone flight, for example. So we can harvest some metadata from the cruise logger into our own system. Files are also automatically created on board for each of the Niskin bottles attached to the CTDs, and these files state the depth that the water was collected at for each bottle. so we can harvest some metadata from these files too into our logging system. The researchers then just need to log each of the water samples that they collect from each of the Niskin bottles. At the end of each cruise, I get sent all of these logs. I look through them all, discuss with the researchers, and make any small manual changes that need to be made. Then, I feed them all into a single PostgreSQL database. After this, we have metadata related to all the records that have been made across all of the cruises across the entire project in a single place. Now, the scientists work really long hours when we're on board. They're exhausted, and this is just another task on top of all of their other tasks. So, some errors creep in. But fortunately, we know that the metadata related to these activities at the top of the pyramid are reliable because they've been harvested automatically from another logging system. Now, the samples should share a lot of the same metadata as the parent activity that they've been collected in. Now, things like the coordinates, the time, the station name, they should all be the same. So, because we've logged alongside each sample the ID of that parent activity, it's possible for us to copy down the metadata from the parent activities to the samples and correct any mistakes that have been made. After all this is finished, the metadata catalogue is hosted on the SciOS webpage. We now have a searchable record of all the samples collected from all the cruises. Anyone can now search for all the samples collected on a certain day, or from a certain station, or all samples of a certain type. This can be used to make researchers aware of what data other people in the project are collecting, so they can collaborate and plan what needs to be done on future cruises. It's also possible for researchers to come to this site and retrieve all the updated and corrected metadata for their own samples. They can just upload a file that includes some event ID column, and all the metadata from those event IDs will be pulled into a new file that they can download. If the input file also included a column for the data, the output file will place this updated metadata alongside that data. The output file is then the data alongside rich metadata that's standardised and already considers many of the standards that people must consider when they're publishing data. It's therefore far easier to convert these files into netcd-fcf files or Darwin Core archives that are compliant with the FAIR data management principles. I've been really lucky to be given access to a lot of great footage to use in this video. Most of the footage from Northern Barents Sea, or from Kronpins Håkon, or from scientists recording data was taken by Christian Morel, unless I've overlain someone else's name somewhere else on the footage. If you're interested in footage like this, you should check out Christian Morel's website at christianmorel.net. If you're interested in the details of how the logging system works, all the code is open source and available on GitHub under the SciOS group, and you can get in touch with me if you want to know more. But until then, I'll leave you with this summary of how the system works. Thanks very much for watching.